In the name of the Father, the Son, and the Holy Spirit. O Lord, send forth your Spirit, and we shall be recreated. You shall renew the face of the earth. Amen.
Amen.
Good morning, everyone, and welcome back. Here we are in the course on environmental bioethics in the program of the Masters of Science and Bioethics at St. Thomas University. And today we're going into lecture 2, which is the atmosphere. Last week we covered the the geosphere. So we're looking at the two spheres, if you will, the geosphere, the atmosphere, and the hydrosphere. I don't know why I'm doing atmosphere before hydrosphere, really. It makes sense logically after the crust to look at the hydrosphere. Maybe for next time I'll reverse the lectures, lecture 2 and 3, to have hydrosphere first and then atmosphere. I don't know. Anyway, so I want to clarify two little things from last class, just to be clear, because I noticed on the summaries, many of you, or some of you may not have been clear about this, and maybe I didn't express it correctly. First, with regards to liquid water on Earth, right? Speaking of the hydrosphere, liquid water on Earth is a tremendous advantage for life as we know it, because organic life as we know it is at the chemical level is a extremely complex series of chemical reactions that we call metabolism. All right, and that is an orderly fashion of chemical reactions and controls, catalytic controls and so forth that make possible life precisely on Earth. And that needs to occur in a liquid soup, as it were. And so water, as we'll see next lecture, has some very unique properties that allows for these chemical reactions to occur. We can say overall that water is benevolent, is very benevolent, because it allows these reactions to occur within it, all right? Itself, water maintaining kind of its neutrality. And so, but the range of water to be liquid, in other words, not solid as in ice, and not vapor, as not gas as in water vapor, all right? Then it's a very narrow range of temperature, which in centigrades is between 0 and 100 degrees, all right? And that's why it's called centigrade, also Celsius, because it's in multiples of 10, right, in the metric system. What's the equivalent in Fahrenheit? Anyone know the two extremes when water freezes and when water evaporates in Fahrenheit? Anyone?
I don't know in Fahrenheit. I know it in degrees.
Again, please, it's a little blurry.
I'm sorry, I was saying I don't know I don't know what the amount would be in Fahrenheit, but I think we all know what it is in degrees.
Yeah, okay, so the amount in
32 and 212, right?
Right, 32 Fahrenheit, positive, okay, not minus 32, but plus 32 Fahrenheit, water freezes. So plus 32 Fahrenheit is equal to 0 centigrade, all right? And then 212, you're right, 212 Fahrenheit, water boils, which is the same as 100 centigrade, all right? Different scale, but the heat amount has to be the same, obviously, just different scales. So more or less, it's not exactly linear. The relationship between Fahrenheit and centigrade is not linear, but it is approximately, very approximately double Fahrenheit to centigrade, you know. So again, we can see, especially for boiling water at 100 degrees centigrade, We're talking about pure water, okay, without any contaminants like salt or anything like that. So 100 degrees centigrade or 212 Fahrenheit. Similar for kind of body temperature, more or less, 37 degrees centigrade, 37 degrees centigrade, close to 40, right? So double 40 is 80. And actually the body temperature in Fahrenheit is what? The temperature, normal temperature, no fever on the thermometer, Fahrenheit, about 97, right? 96.8 or whatever, 97. So it's a little more than double. Actually thinking about it, it's almost closer to 3 times. And whether the two scales meet, by the way, the two scales, Fahrenheit and centigrade, meet, in other words, they have the same number. Anybody know? Just curiosity. These are trivia facts. Well, trivia for us, but it could be relevant for other people, scientists particularly, who are working in this stuff, or maybe engineers looking at alloys and whatnot. They meet at -40. So -40 centigrade is the same as -40 Fahrenheit. Okay, it's the same amount of heat. But then from there, going up or going down, they diverge. Okay. All right, so liquid water, the main reason for having liquid water on Earth is not necessarily the distance to the sun itself. All right, it's not. Because if it were, I was just looking at something just before class here, the inner planets, I hope you can see the screen. Can you people see the screen, my computer screen?
Yes, Father.
Okay, thank you. So you see here's Earth, and we got Venus and Mercury, which are closer to the sun. Of course, this diagram is not to scale, okay? It's not to scale, because if the planets were actually this close to the sun, well, first of all, we would be sucked into the sun because of gravitational pull. And if we weren't, we would be melted and set on fire by the sun heat, because it would be just too close. So this diagram is not to scale, okay, the distances. It's just to show rather the sequence or the order of planets from the sun out of our solar system. Anyway, Venus and Mercury are closer to the sun than we are. So by that logic, you know, they should have water vapor. And well, Venus has apparently very, very little water, so it's hard to tell. But Mercury may actually have frozen water just below the surface, you know, and by this count, it should have just boiling water, water vapor, but it actually maybe there's some evidence that it has frozen water just before the surface. Okay, so what's keeping water liquid on Earth is rather the internal temperature, which makes it even more interesting. The internal temperature, which is the radiation from the core, which, by the way, we have 2 layers of core, all right, but the inner core is actually solid because it's kind of pure, just mostly iron and nickel, and is white hot, but it's solid. And it's solid because of the gravitational pull on it, on the atoms, on the actual atoms of iron and nickel, which tend to be rather large atoms. Ferrum is iron, comes from the Latin, well, actually 26. Nickel is 28. So, all right, they're intermediate actually under atomic number. But the fact that they are toward the center of gravity, they have the largest gravitational pull on them. And that's what makes the inner core solid, all right? And white hot, which is beyond red hot. It's hotter than red hot. Then the outer core is liquid. These are, of course, indirect measurements because no one has gone down there with a thermometer. So they're indirect measurements mostly from the reflection and the refraction of the seismic waves going through the Earth from the epicenter to the opposite side of the Earth. And that in itself is done, it's an extrapolation of some bench experiment that has been done in a lab, taking, you take iron and you heat it up to white hot, so we can heat iron experimentally in a lab to 6,000 degrees, all right, and then run the equivalent of seismic waves through it to see what the reflection and the refraction is. And then we extrapolate that number or that measurement to what we detect experimentally when these seismic waves happen on the Earth, actually in live, in vivo. Okay, so then the outer core, we're still on the core, is liquid. So in other words, is far enough from the gravity to actually flow and to move a little bit, all right? The inner core is so, please.
Oui, c'est ça, c'est la convoquée.
Sorry. Okay, so we're clear about the core, right? Then comes the mantle, upper and lower mantle. The lower mantle is more fluid than the upper mantle, and that has to do with a combination of the heat, which is now not quite hot, but red hot. It's a little less hot, still thousands of degrees, maybe about 3,000 degrees centigrade, all right? And it's fluid because it's far enough away from the core gravitationally to allow for fluidity, for movement. And that's where the convection currents are occurring, the upper and lower mantle, to cause the continental drift, okay, and plate tectonics. But it's much more, so it's homogeneous in its composition in the big picture, but it's made up of many, many elements and molecules, not just nickel and iron. Okay, rather the nickel and iron tend to be sucked into the core. So the mantle is a composition of many, many other metals and non-metals, elements in general. All right. Then the upper mantle seems to be a little more brittle, and it's kind of a transition between liquid and solid, but there's still fluidity. Otherwise, we wouldn't have continental drift. And then the thin layer of crust, which is actually solid, mostly rocks, the various types of rocks, mostly three types: the igneous, the sedimentary, and the what's the other one? Igneous, sedimentary. There's a third type of rock. I can't remember right now. But anyway, that crust, that thin layer of crust, actually acts as an insulation, because on the bottom side of the crust, meaning the upper mantle, we're still in thousands of degrees centigrade, like 2,000 more or less, something like that. But on the outside of the crust, basically where we're standing, the surface of the Earth, we are typically within decades, in the tens of degrees centigrade and Fahrenheit, all right, in the tenths, the units of tenths, like 20, 30, 40 degrees Fahrenheit, centigrade, more or less. It's that order of magnitude. So we are 2 orders of magnitude cooler on the surface of the Earth than at the bottom of the crust, the one that's touching the mantle. You get it? And it's that, so basically the crust of the Earth serves as an insulator, but in reverse, from extreme heat to very little heat, all right? And that allows for water to be liquid. on the surface of the Earth. And that's basically it, because then as we move out of the atmosphere, say into the space that is near us, it's extremely cold. All right, it will be hundreds, if not thousands, at least hundreds of degrees below zero. So water would freeze, leaving the atmosphere of Earth, which is again a very thin layer of gas, basically, around the Earth. And that's what we're going to get into today. Right. So the reason for having liquid water on the surface of the Earth, which allows for life, is basically the crust, the formation of the crust, which is a gradual process over millions of years of dissipating heat, right? Of losing heat.
Father, this is Jose, a quick
Hey.
question pertinent to that.
Yep.
I've heard discussion on global warming,
Mhm.
that global warming has created a loss of surface water. So there's some drying of the rivers and lakes and so on. But wouldn't that be related to change in atmosphere and decrease in the protection from the heat of the sun? And that has raised the overall temperature? Because
Right.
what you're discussing, that if it's only inner, that would mean that the inner core would be getting warmer. And that's what's causing us to lose the surface water.
Right. Okay. So this is truly an example of complexity, right? A complex system, and actually complexity of complexities. And that's precisely, it's a good segue into today's lecture, because I pull up the last slide, or the next to the last slide, the distinction between weather and climate. All right. So we have orders of magnitude here, and a lot of it has to do with the time scale that we're talking about. So global warming, which now a number of scientists are walking away from global warming as such, because what we have is mostly regional warming, overall global warming, perhaps, but also associated with climate change, and the implication of climate change in today's connotation, right, in today's language and media and so forth, is that the planet as a whole is getting warmer, right? So we would be heading to what we call a tropicalization of the Earth, tropicalization, okay? But again, the scale is, climate is measured minimally in thousands of years, and more comfortably in hundreds of thousands of years. So you see the scale, the time range is a long range. Even so, the heat dissipation of the Earth from the core out to the crust, and beyond the crust to the atmosphere and out into space, which is essentially that general dissipation of heat from any object that is hot, right? Whether it's a planet or stars, and globally, more as a cluster galaxies, that is radiation, heat radiation, which increases entropy, right? Energy that is unavailable for work. That is measured typically in millions or billions of years. So again, the scale is not only large, it's super large in reference to time. Then reverse that or crunch it down to a lifespan, which, 100 years for a human being is a long time, right? And how long has the thermometer been around to actually measure the temperature of the atmosphere? Perhaps a few hundred years, which again is in the magnitude, the order of magnitudes of 10 to the 2, right, in the hundreds. But climate change is 10 to the 4, 10 to the 5, and then heat radiation from massive objects like planet Earth is 10 to the 7, 10 to the 8 magnitude, right? So the orders of magnitude are different. And that's the challenge. The bottom line is that we use models to estimate, but the margin of error of these models is fairly large, okay, the margin of error, because it's based on very scant data. And most of the data is going to be actually indirect. Indirect meaning measuring CO2 bubbles trapped in ice cores. All right. So talk about estimate, very rough estimate. But anyway, so we have to be careful, what is the cause and what is the effect here. This radiation, heat radiation from the core out into space is a very, very slow process, typically in the millions or billions of years, okay? So just to say that the order of magnitude of what we're measuring can make a difference. Okay, so I'll leave it at that for now, but the whole course, this whole course in a big way is trying to estimate this global warming in quotations and more significantly climate change, all right? Also, giving you a couple of punchlines here, we know that the climate, not the weather, but the climate has been changing on Earth over millions and billions of years, all right? From full ice age, what we call a winterization of the whole globe, where most of the water on Earth would be solid, all right? Well, at least a lot of the water on Earth by way of ice. Those are the ice ages. And on the extreme opposite is what we call a tropicalization of the Earth, where practically there's no natural ice. In other words, the North Pole and the South Pole, and obviously other glaciers melted, which will increase the sea level and so forth. That would be a tropicalization of the Earth, all right? We've had evidence of that, of at least of 5 of them, 5 of these cycles in the past 500,000 years, which is not that long. Okay. Long-winded, indirect answer to your question, but more to come. Stay tuned.
Thank you, Father.
Okay. All right, let's go back into the lecture here. Again, so we're going to cover a little tiny review of mass, weight, and associated with that matter energy, because I don't want you confusing both things, okay? Then fluid dynamics, going to get into fluid dynamics. Then natural composition of air, the air that we're breathing around us. Stratification of the air, meaning the atmosphere as a whole, the different layers of the atmosphere. Just like the geosphere has layers, the atmosphere also has layers, and the hydrosphere also has layers. Barometric pressure, to understand what that pressure means, and it's associated with gravity, affecting gas molecules. Wind patterns, which is what creates our climate. All right, sorry, what creates our weather, then distinction between weather and climate, and the natural right to clean air so we can breathe. Okay, so just very brief review between mass and weight. Remember that the weight, right, is mass times gravity, mass times gravity. Now, in the metric system, which is what science has used, time out for a moment, let me turn off the lights here. So, got one customer came present, physically present, all right? So, anyway, the metric system, which is what is used universally by scientists, because it's in increments of 10, right? 1, 10, 100, 1,000, etc. Is we use grams or kilograms. Keep in mind that for mass, for the unit of mass is the gram, which is very tiny. A gram would be like a grain of sand, would be a gram. So an easy measure for us is a kilogram or a kilo. But the kilogram, even though it's more popular for measuring because of our scale, right? Our scale, we measure our weight in kilograms, right? If we measure it in grams, we have to multiply it times 1,000. The kilogram is not the unit of measure of mass, all right? We have to be clear in science, what is the unit of measure? So the unit of measure of mass is the gram, which is very tiny for our human body scale. So a kilogram is 1,000 grams. Typically, we refer to it just as kilo, which is a 1 kilo, which is a contraction, right? And it's about 2 pounds. So 2 pounds, 2.2 pounds is 1 kilo. All right, 2 pounds. And if you want to convert to liters and gallons, so a pound more or less is a quart of a gallon, right? A quart of a gallon, so it's about 1 liter. All right, so that's a unit of mass, which is universal, meaning that the mass of an object in any part of the universe is the same. It's intrinsic measure. All right. Now weight is different because weight we have to account for gravity, which is a force. A force is kind of a esoteric thing, you know, because a force is a pull or a push. If I push on the wall with my hand, I'm generating a force on the wall. All right. And so the force itself, in this particular case, there are different types of forces. Gravity is a centripetal force. It's a force that pulls towards the center. There are other forces that are centrifugal that tend to flee from the center. As an object, when an object is rotating, it tends to flee from the center. That is centripetal. It tends to go away from the center. In that case, it's opposite to gravity. But gravity at the surface of the Earth is this 9.8 meters per second square. So the second square makes it an acceleration. All right, makes it an acceleration. Now you can say it's a constant acceleration instead of a change in acceleration. I use the speedometer on the car, the cruise control, right? That is a constant acceleration. So we have constant speed, velocity, then we have constant acceleration, and then we have acceleration of acceleration. And that's when we get into the meter square per second square. That would be an acceleration of an acceleration. You know, it's accelerating every minute, every meter, all right? And that was, so C square makes that acceleration of an acceleration. So when we multiply the mass times the gravity of whatever system, it could be the Earth system, or it could be on Venus, or it could be in the moon, for example. You know, the moon has a smaller gravity, right? Why would the moon have a smaller gravity? It's a combination of two things. One is obviously the size, right? But the other one is also the composition of the moon itself, the composition, which I think it has more or less the same composition, the actual physical chemical composition of the moon, the material composition of the moon is similar to the Earth, right? So it's and the size. So quality and quantity, gravity of moon is going to be much less than Earth. Look at that, 1.6, right? As opposed to 9.8. So it's almost 1/10. It's almost 1/10, between 1/5 and 1/10, the pull of Earth. So we would weigh less. We would weigh about 1/10 less on the moon, right? But the mass would be the same. The mass would be the same. All right. By the way, the units for weight is newtons, in honor of Isaac Newton, who is the one who came up with the constant, the gravitational constant on the surface of the Earth, right? And so 1 Newton then is 1 kilogram times meter per second square. Here's the acceleration, here's the gravity, all right, and here's the mass. And it's 1 kilogram. So it's 1,000 grams if you want to put it in mass units, would be 1,000 grams. Don't confuse mass with little m here, right? Because in Einstein's equation, E equal mc squared, that little m is not meters, is mass, all right? Should have used capital M, but they used little m. So this little m is the units, it's meter. Whereas in Einstein's formula, E equal mc squared, that is actually mass. And with regards to that formula, E equal mc squared, what I want to say about that is that it's not like there's a mass energy equivalence, all right? So the sum total of the universe has to be always 100%, the sum total of mass and energy. But the actual mass component of the universe, at most is about 32% estimate. How am I coming up with that number? The mass of the universe. Of the 100%, about 32%. I'm adding 2 smaller percentages, which are what? From last lecture. Has to do with visible and dark.
And
Energy.
mass and energy?
Yeah, but which one? Okay, so the adjective
Oh,
is
so
different.
you,
All right, let's start with the bigger of the 2 smaller numbers is 27%, which is dark matter, right?
yes.
Dark matter, is dark matter dark energy? No, it's not. It's either matter or energy. Okay, so dark matter is dark matter by measurement for the 27%. And it's an indirect measurement because we cannot measure it directly, all right, at least for now with the instruments that we have. But the core of black holes, for example, is a good example of that. But we can measure it indirectly because we see in the stellar, the constellation, we see a hole that is dark, right? That is black. So there's the images here. These are too big. Just looking for, yeah, right. Okay. So here are all these dots, all these white dots. I hope you can see the little hand. Can you see the little hand going around? Anyone?
Yes, Father.
Pointer. Okay, thanks. All right. So all these that we would call stars, they're galaxies. Okay. A star, the sun is a star unit, a single one. So our sun is a star, which is a ball of gas that is on fire. It's red hot. It's yellow, red hot. All right. And so the sun right now is about halfway its lifespan, about 4.5 billion years, right? So it started as white hot, then it lost a lot of heat, and it went to red hot, and eventually it will die out. Okay, it will implode and then explode and disappear, basically. And the remnants will form other systems. But basically, the sun is a star, and the little dots that we're seeing all around here, these are not stars, these are millions of stars, or maybe billions, forming galaxies. So actually, these dots are galaxies, and there will be billions of galaxies in the universe, all right? But you see, then all of a sudden here in the middle of the photo, this is a photograph, there's a black hole. All right, it's a black circle. And the implication here is that at the core of this sphere, is a massive object that is so massive and so dense that not even photons are able to come out, right? They're trapped. They're trapped. So the gravity is unbelievably high, the gravitational pull, sucking. And that's why it tends to suck everything that is around it too. Now, we don't know exactly how distant this thing is from us, right, from the camera, but there is a background. These galaxies are beyond the black hole, are in the background, all right? And the black hole is in the foreground. Beyond that, there's also a lensing effect that is done here because of the reflection of the light of the photons that are coming from the galaxies that are behind the black hole. There are galaxies behind, right? And when those galaxies are emitting photons, the photons that are coming our way, right, into the camera are being deflected by this lensing effect that is done at the perimeter, something kind of parallel, analogous to what occurs with our atmosphere when the sun is setting and the rays of the sun come through more atmosphere, right, on the horizon. And that's how we can measure it indirectly, all right? So that's the 27%. If we add up all the black holes that we estimate are out there, again, it's a very rough estimate, and we estimate that pretty much at the core of each galaxy will be a black hole, all right, including our own galaxy, which is the Milky Way. Which, by the way, the Milky Way is the name of our galaxy, one of these millions of dots, right? So at the core of galaxies, typically there will be a black hole, but the galaxy itself is made up of millions of planetary systems, okay? At the center of each planetary system is not a black hole, it's a sun. And then planets around it. Some suns, some stars have planets around them, other stars don't have planets around them, all right? So they don't have a planetary system that we know of. But different places. So you got to place the black hole where it belongs, which is at the center of galaxies generally. The galaxies themselves are made up of millions and millions of solar systems. Okay. All right, so that's to clarify a little bit stuff that I saw on the summaries. Enough. Let's go forward. Otherwise, we'll never end. Any questions or comments there? I know that the magnitudes are huge, humongous, immense, you know, but we can at least think about them intellectually, and we have some glimpse from the photos that are being taken. Of course, up until now, the best photos have been taken by the Hubble, which is a telescope that is outside the atmosphere and the outer atmosphere of Earth, and therefore able to take photos without the interference of the atmosphere. The atmosphere filters a lot of light and photons and distorts them. So it's a great advantage to get out of the atmosphere for photographing the universe. And that way we avoid all this filtering. It's like having a camera that the lens is full of mud, right? It's not going to give us a clear image. So getting outside of the mud, in this case, our atmosphere, the Earth atmosphere, gives us a clear, brighter picture. However, the Hubble is limited because it was, I think it was in the 50s that was launched, maybe the 60s, I don't know exactly. But that was the top technology at the time, all right? And I mean, think about it, in the 60s, computers were barely coming around. I mean, a computer was a huge thing, looked like a refrigerator. They're called univacs. They were immense. Our cell phones today have maybe 1,000 times the power that those univacs had, all right? And it's down to a pocket size. Can fit a refrigerator in a pocket. So that was the technology available at the time. Imagine by our standards today, that was primitive, right? And so the Webb, the James Webb with 2 Bs, look it up, was launched a couple of months ago. And that is, like 1,000 times more refined than the Hubble. And it's out there and it's gone into deeper space, well, further out from the atmosphere, actually into space, and is taking spectacular, very crisp photographs. Why don't I just go there? Web photographs.
Father, when you look for that, I want to ask you, so the Hubble, okay, whatever, so what, 70 years ago, everything that we know now is being discovered or understanding because of that telescope, or the new technology is helping?
Most of it, not all, but I just want to see when Hubble was launched. I mean, these are the pictures that Hubble was taking. Look at that, fantastic. But when you blow this up, you lose resolution. It gets pixelated, right? You're familiar with pixelation. There's the Hubble. It looks spectacular, but this is the Webb. The James Webb. So here was the Hubble, here is the Webb. Interesting, they're kind of about the same size. I thought the Webb was much larger than Hubble, and it's not. But anyway, it's much more refined, and can measure a much broader range of light spectrum, number one. Number two, the resolution is many orders of magnitude better, okay? So where was I? I just want to see when the Hubble was actually launched. Come on. Okay, I don't want to waste time in that. Maybe someone can look it up in the meantime. Tell me when the Hubble was launched. But Webb photos. Yes, these are some of the Webb photos that are coming out. The resolution, well, we compare it to a Hubble photograph, the resolution is just spectacular. It's much, much greater. For example, here we can actually see galaxies. What used to look like stars, here we begin to see, stop. Turning. Yep.
This is April 24, 1990.
1990. Wow, that recent. I thought it went back to the 60s. Okay, well, my bad. Okay, here, stop there, stop. You can see actual galaxies, right? These would look like little dots on the Hubble. They actually look like galaxies now. The planet, the disk, the galactic disk with the Webb. So anyway, several orders of magnitude better than the Hubble. And actually just like 30 years later then, all right? I thought it was older.
So it says that it was conceived in the 1940s, but it was launched April 24, 1990.
Okay, all right, thank you. Very good. So don't confuse or say, yeah, that 32%, let me go back. Sorry, let me go back to the 32% for a moment. The 32% is dark matter, 27% approximately, plus the visible matter energy combined. Again, because of Einstein's formula, at least visible matter energy, in other words, measurable, I should say measurable better, okay, empirical matter / energy, we're lumping it together. Because again, with the Einstein's formula, we can convert measurable mass energy back and forth. So we can lump it together as a single reality, all right? That's the 5% of the known universe. So 27 plus 5 is a 32. That's what I'm saying, that 1/3 of the universe is combination between dark matter and light mass energy, or matter. And then dark energy, right, is that other 2/3, I said the 68%, the other 2/3 of the universe, which is a different we're using dark in a different way there. We're using dark because we're in the dark about it. In other words, we don't really know what it is or how to measure it. But the scientists, the astrophysicists are telling us it's mostly energy as opposed to mass. Okay, now we may be getting into a surprise when eventually we develop some instrument that can measure some of that dark energy, all right, and realize that there may be a mass energy conversion there too, but we don't know if the mass energy conversion applies to the dark matter and energy, all right? Most likely it may apply at least to the dark matter because we know that there's got to be some gravitational field at the core of the black hole. And that gravitational field, the only thing we can think about is highly, incredibly dense matter. But matter, known matter, in other words, matter that is made up of elements, you know, like the core of the Earth, nickel and iron. In our case, different planets are made up of different elements, okay? But elements on the periodic table. It could be that we discover other elements that we don't know yet. That's also possible. Okay, so it gets fuzzier and fuzzier as we get out. However, what is giving us the 100% is that background radiation, the microwave radiation, right? The background radiation, which is supposed to be what is left from the residue from the Big Bang, okay? Background radiation. This guy, cosmic background, right? Cosmic background is supposed to be what's left over from the Big Bang. Kind of, in a very crude way, the smoke and the dust that is left after an explosion, all right? Okay. Let's go forward, get into fluids. All right, so fluids are the other two states of matter that is not solid. It's not solid. So what are the other two states that are left? Liquid and gas. All right, liquid and gas, precisely because they're not solid, they flow. Now, of course, water, we know that water flows. We can pour water from one glass into another and we see it flow, right? Like a river and so forth. But some people are not as aware that gas also flows. Gas is also a fluid. If gas were not a fluid, birds couldn't stay on the air and airplanes could not fly because the basic aerodynamics of wings is to make the air below the wing go faster than the air above the wing. And that's why the wing that has that curvature design, whether it's on a bird or on a plane, has a little bit of a curve, especially on the top surface of the wing, right? So that makes the air below the wing flow faster than above the wing, and that allows the wing to stay airborne, literally above, and not being pulled down by gravity, okay? So air flows. There's another little experiment that you can do easily at night, all right? And I call it to see what you don't see and you don't see what you see, all right? Take a candle and light it at night, and the light's on in the room. So you need a candle, you need a match or something, or a lighter to light the candle, and you need a flashlight. And you need to be inside a room that you can turn the light on and off, all right? So at night, you go into a room with a candle, lighter, and a flashlight. And with the light on, you turn on the candle. You light the candle. So what do we see? We see the flame, right? We see the flame. So, and we don't see the air around it. We don't see it when there's light in the room. Okay, by the way, the flame is that fourth state that we call plasma. Unstable because it's dynamic, it's burning. As soon as it runs out of wick, that flame stops. Or if it runs out of oxygen, it also stops. All right, that's why it's unstable. So night in a room that is lit up, that the lights are, the electric light is on, the candle is on, we see the flame and we don't see the air around it, right? Now, keep that candle lit, turn on the flashlight and turn off the light in the room. Shine a light through the candle onto the wall. Shine the flashlight through the candle onto the wall. And what do you see on the wall? I'll leave it there. Do the experiment and you can tell me next time what you see on the wall, okay? So when the room is lit with ambient light, we see the light, the flame, the fire, and we don't see the air around it. And when we do the experiment, it will be reversed. We'll see what we don't see, and we don't see what we see. Okay, check it out and get back to me. Get back to us. So fluids, some properties of fluids, they take up the volume of the container, but only the bottom of the container. All right. So, for example, in contrast to solids, solids hold their own volume. Right. If I put a marble on top of inside a dish, the marble doesn't melt on the dish, right? The marble maintains its own size, its own shape. So solids maintain their own shape. Liquids don't maintain their own shape. They take up the shape of the container, but basically kind of the bottom of the container, all right? Gases take up the volume of the entire container. So if the container is not closed, the gas will escape. But if the container is closed, then the gas will take up the whole of the container. If we think with our mind's eye, right, because we can travel anywhere with our mind's eye, what is happening, the liquid, the molecules are in a dynamic state, they have more fluidity, right? They have more fluidity. The molecules are not tightly together, like in solids. The molecules are still vibrating, but they don't have much wiggle room. But in fluids, the molecules have more wiggle room. So in fluids, the molecules are kind of sliding on top of each other in a liquid, and so they can flow. But in gas, there is essentially no attraction between molecules. There's no attraction between molecules, so the molecules in that gas are free to bounce around and move in a random motion and bounce against each other and bounce against the inner surface of the container, all right? And so that's why they take up the volume of the container as such. And we give it enough time, a few seconds, you know, they form a homogeneous distribution. So any molecule can be at any distance from any other molecule from the surface, from the inner surface at any one time. So they take up basically the volume of the container. They don't hold their own volume. They don't hold their own shape. Both liquids and gases, but gases more than liquid. What's interesting to study, by the way, is the interaction between the liquid and the gas, the surface, all right? We'll get more into that in the next lecture in the hydrosphere. All right, so what affects the volume of gases, also of solids, but more liquids and gases. The volume is more affected by heat and or pressure, and they cause essentially the same effect. The more we heat a fluid, the more it expands generally, all right? Whereas the more, so these are inversely proportional. The more pressure we add on a fluid, the more it contracts. So for example, we can go from liquid to gas by heating up the liquid, all right? It's called evaporation. So when we heat up water to 100 degrees centigrade, the water evaporates. Essentially, we have provided enough activation energy, activation heat, so that the molecules dissociate with each other. The water molecules dissociate, and now they go into space, and they start flying around as a gas, right? They dissipate. When we do the opposite, when we cool a gas, we can liquefy a gas. All right, so we can take water vapor and condense it. If we bring it below 100 degrees centigrade, it will start condensing into liquid, and that's condensation, right? We can do the same with pressure, but in the reverse. So in other words, if we compress a gas, we can liquefy it. And if we take off pressure, right, then that liquid can turn into gas. Pressure is generally more intense than the amount of heat that is needed to cause the same effect, all right? Also, while we're at this, I want to mention, well, I'll leave that for when we get to the next lecture on the hydrosphere. But in nature and in the natural system of Earth that we're studying, the big picture, the two fluids are the hydrosphere, meaning all the water, the natural water on Earth, that is liquid, mostly the oceans, also rivers and lakes and so forth. And then the gas stage is going to be in the atmosphere, including water vapor, right? So we have the same molecule, if you will, of water that can either be in the hydrosphere or the atmosphere, and there is a cycle that goes back and forth, basically cloud formation and precipitation, otherwise known as rain. That is a cycle that will be in 2 lectures. All right, so the takeaway message here is that both gases and liquids are fluids, and so they flow. It's less evident for air, more evident for water or liquids on Earth, all right? But the atmosphere is a fluid, basically. The atmosphere is a fluid. Okay, another little basic terminology here, just a nomenclature: all matter or mass. It's either pure or mixed, right? These are categories that are mutually exclusive. So when they're pure substances, they can either be elements or compounds. Compounds are made out of elements. For example, this is showing typically a water molecule, all right, which has 2 hydrogens and 1 oxygen. But if it's elemental, right, if the pure substance is just elements, then it's elemental, it's not a compound, okay? Most substances on Earth are actually, that are substances, right, are compounds. But sometimes we find elements just by themselves. As in the case of the atmosphere, for example, pure oxygen, which is diatomic, H2, or pure hydrogen, oxygen, O2, or hydrogen, H2, those are elemental. Now, compound could be, for example, CO2, which is carbon and oxygen, all right? Or H2O, those are pure substances that are compounds. On the other side of the bag, the other bag is mixtures. Mixtures can be homogeneous or heterogeneous, all right? And homogeneous mixtures are typically solutions like salt, sodium chloride mixed in water. There's a homogeneous mixture between the water molecules and the salt molecules, all right? And that's called typically a solution. Or if the mixture is heterogeneous, then it's not a solution, but it is a, what's the other name? The mixture, a heterogeneous mixture. There's another name for heterogeneous mixture that is not in suspension, a suspension. All right, so like sand, for example, in water, you mix it up, you shake it, and the sand particles will wiggle around for a while, but after a little time, the sand will settle to the bottom, not go into solution, all right? And so it's heterogeneous. You get the water column and you get the sand underneath. And so that is called a suspension, not a solution. Okay, so that basically means what substances, either elements or compounds that are soluble in water or not, or they can be soluble in another solute, which could be, for example, alcohol. I'll talk more about this in the hydrosphere. It makes more sense in the next lecture on the hydrosphere. Let's look at the composition of the atmosphere, the chemical composition, the gas composition of the atmosphere, right? The air that surrounds us. It's mostly nitrogen, almost 80%, right? Almost 3/4 of the atmosphere of the air that surrounds us right now is nitrogen, which is N2 diatomic, 2 atoms of the element nitrogen together, they stabilize each other. That's called diatomic, diatomic. Diatomic nitrogen, diatomic oxygen, diatomic helium, and hydrogen, etc. Then the other almost 21% is oxygen. The other 1/5, okay, is hydrogen. Again, diatomic, O2. These are all gases, gas. Then the 1% that's left, or let me see, 78, 21, about 1% that's left are these other gases, of which argon is the largest one. Again, gas, this is all gas. Argon is the last one, and the largest one, almost 1%. And the others are these trace elements, trace meaning that they are minute quantities, typically 0.0001, 2, 3, in centesimals or millésimals. CO2, which is an infinitesimal quantity. It's amazing. I put it here. Is this one is the same CO2. I put it here so that you can see this is 0.04%. This is a centesimal. This is a decimal. This is a centesimal. The next one over 0.00 would be a millesimal. So it's a centesimal quantity, much less than 1%. And it makes a big difference. It's actually measured in parts per million or parts per thousand. All right, we'll get to that scale. They're part of the trace elements. CO2, neon, helium, methane, nitrous oxide, this is NO2, and ozone, which is O3. O3, 3 atoms of oxygen in the stratosphere. All right, so you see that most of the composition of the Earth's atmosphere, which is the air that we're breathing right now, about 20 times each minute, in and out, 20 breaths per minute, it's mostly nitrogen. Then 1/5 of it is oxygen, and then the other 1 to 2% is all these trace elements. Oxygen is obviously needed for cellular respiration. So oxygen is absorbed by the alveoli on the lungs, and then it goes into the circulatory system, the blood, specifically the red blood cell, the RBC, which has a nucleus of iron, precisely, Fe, iron, ferrum, and that nucleus oxidizes with the oxygen, so it turns into FeO2, ferrum oxide, oxygen oxide, and is transported from the lungs to all the tissues of the body for cellular respiration. At each cell of the tissues, the oxygen gets off the ferrum, gets off the iron, all right? and goes into the cell and helps with metabolism, cellular metabolism, specifically recharging ATPs, adenosine triphosphate, which is the energy molecule of each cell, of the trillions of cells that we have in the body. That's for metabolism, for life, right? And then the product of that cellular respiration, which is a tiny burning effect, that cellular respiration, the product gives off CO2, carbon dioxide. That carbon dioxide again hitches a ride with the same ferrum, with the same RBC. So it forms now FeCO2 and heads back to the lungs to be expelled by expiration, by breathing out, right? CO2. So we inhale oxygen and we exhale CO2. And the transport system is the red blood cell in the blood. And what makes it red is precisely when it oxidizes, when the iron oxidizes with the oxygen, right? It turns reddish, just like rust, when we take a piece of iron and expose it to the atmosphere, over some time, it will rust and turn a reddish color. That's what gives the blood its reddish color, okay? All right, so how about the nitrogen? We're breathing nitrogen also, and we're breathing mostly nitrogen. Does nothing. It's called inert. Nitrogen gas comes in and out of our lungs and does nothing. Thanks be to God, because it's in gas form. If it were not gas, then it would have an effect. Or if under pressure, that gas goes into the blood system, like for example, in scuba diving, then that can be dangerous because that gas, when we change the pressure on the body, that gas will then expand inside the body and cause embolism, cause clots, all right? And it's a very dangerous situation. That's a whole issue with scuba diving of compensating and decompressing as the diver comes up to the surface from the bottom of the ocean or under the water column is under pressure, okay? The breathing compressed air. So anyway, nitrogen gas is inert, comes in and out of our lungs and does essentially nothing. And the other trace elements also basically come in and out. Some may have more of a toxic effect than others. But the main component here that we breathe is the oxygen. All right, continuing here on the scale for CO2, because this is going to have implications for climate change, right? The main culprit for warming of the atmosphere right now, the main culprit is CO2. CO2, because CO2 has a high heat capacity. It retains heat, and it causes what we call greenhouse effect. Greenhouse effect is that it warms the atmosphere because the CO2 molecule itself retains heat. Water molecule also retains heat. Methane also retains heat. In fact, methane retains more heat than CO2 per volume. So methane is even more dangerous than CO2. The good thing is that there's much less methane gas than CO2 gas, all right? So just for now, I want to introduce this little diagram here, the scale that we will use later in the course to talk about global warming and climate change, right? But basically, the scale is what I want to measure. The scale is typically parts per million, all right? ppm. So another notation of the M. So the M is used a lot, little m, lowercase m. We saw it as mass. We also saw it as meter. Now we're seeing it for million, all right? The same lowercase m, so it has to be in context. Has to be in context. Parts per thousand is ppt, so the T is for 1,000, all right? Parts per thousand. So to think of a simple analogy, if we are, last time when I developed this slide, imagine, I had actually six students in class physically here, all right? So we were 6 students in the class, and if there were 1,000 people on campus that day, 1,000 people on campus, we would be a 6 PPT at St. Thomas that day, right? We had six people on, so I had 5 students, myself, we were 6. And there were 1,000 people hypothetically on campus that day, so we were 6 PPT. 6 parts per thousand, just to get a feel for what the scale means, right? Small, but not insignificant. So typical CO2 is measured in parts per million, parts per million. So in 2013, the CO2 in the atmosphere, specifically in the troposphere, which is where we have life, the upper 100 kilometers, it was 400 ppm, 400 ppm. And it's the highest it's been in the past 800,000 years. All right, here's a scale. In 1950, we crossed this threshold of 300 ppt. This scale is CO2 in, sorry, ppm. The scale, the vertical, the y-axis, the dependent axis, right? Dependent on time, is a CO2 measurement in parts per million. The lower end of the scale is 160 ppm. The upper is 480. So it's a range of about 200, more or less, a little over 200 ppms. 300 was a threshold, the highest peak at the, here are the 5, basically 1, 2, 3, 4, 5, roughly. Ice ages would be down here, and tropicalizations would be up here. All right, the highest that we have from the geologic record was here, about 300, a little over 300,000 years ago, at 300 ppm CO2. And in 1950, we passed that threshold, and it is shooting up vertically in a very accelerated way, right? That's the claim for the climate change. That's the claim that this is off the, as I say, Richter scale. It's not a Richter scale, but it is a scale. It's off the ppm scale of CO2 shooting up in just 60, 70 years, all right, to the current rate beyond 400 ppm. 2013 was when it bypassed 400 ppm. Okay, so this is the current warning, challenge, crisis, red flag is the rise in CO2. However, methane retains even much more heat. And the problem with methane is the methane that is held in permafrost, precisely in the tundra. When that permafrost starts melting, that methane is released. And that has, I think, 20 or 30 more times more heat retention than CO2, even though it's a smaller quantity. All right, so it's there held in permafrost for now, but it's beginning to melt. So a second source of global warming. Water vapor also, but water vapor.
CO2 now is 200 and above at this moment.
Yes, it's above, yeah, it's above 200. Yeah,
No,
400 ppm, yeah. It's getting close to 420 ppm, right? Yeah, and there's no sign of it decreasing anytime soon. However, I'll tell you, you know when it decreased? 2 years ago. 2 years ago with the global lockdown.
So you mean with the pandemic?
The pandemic, exactly, because of lack of transportation. So again, we're getting at the sources of the CO2, which is going to be anthropogenic. Anthropogenic is human source, not nature, not a wildfire, not a volcano, but industry. And even more significantly than industry, it's between industry and transportation, including the car that you're all driving, because none of you have an electric car like I do. Okay, so the car that you're driving is contributing to that CO2. But 2 years ago, when there was a shutdown,
I am just living that right now because I'm in Haiti. Everything is shut down.
yes, yes, there you go, exactly at the local level. You are, that was Father Franco, right? You are in Haiti right now, Father?
Yes, I am in Haiti. I came here for my sister's vows. The country is locked with me there.
There's a lockdown. There you go.
Yes.
So you're locked down over there. Yeah, okay. Prayers for you, Father, and your people, okay?
Yes.
So you see how things work. Transportation, global transportation is a significant contributor to CO2 for now. That's the whole issue of trying to get away from fossil fuels and the combustion of fossil fuels. That's a major contributor of CO2 right now. Okay, we'll get into that in more detail. Just for now, I want to introduce it for the scale. Even though in nature, carbon dioxide is this tiny fraction, but an upset, just an uptick in this tiny fraction can have a huge effect on the weather and on the heat, on warming, right? Warming the weather, and perhaps eventually we keep it up, warming the climate because of its high heat capacity of CO2. Okay, let's move a little bit further. Now let's go back to the layers and look at the various, there are 5 main layers of our atmosphere, what we call the atmosphere, beginning from the surface. So this is from the surface out. I should have reversed these names, but think of it. This is beginning from the surface, the troposphere. This is where life occurs as we know it, right? Then we go into the stratosphere. Mesosphere is the middle layer. Thermosphere, because there's an increase in temperature there, and then the exosphere dissipates out into space, all right? It's still inner space, which is within the planetary system. We're still not anywhere near outside our solar system, but it's known as the exosphere, when our atmosphere dissipates out into what we call inner space. Okay. So here are the layers in a diagram: the troposphere, stratosphere, mesosphere, thermosphere, and exosphere, okay? With a few objects placed in their layer. So weather balloons and flights go up to about, you hear about 30,000 feet, right? That's about 10,000 meters. That is, they're getting close to the stratosphere, at the edge of the troposphere and the stratosphere. By the way, the in-between layers, the transition from one layer to another is called a pause, So the first one is the tropopause, is the transition from the troposphere to the stratosphere. Then you would have the stratopause, is the transition from the stratosphere to the mesosphere. The mesopause, from the mesosphere to the thermosphere, and then the thermopause out into the exosphere, and there's no exopause because the exosphere is the last layer, as it were, into space. Okay. All right, the phenomena of asteroids and meteorites that we see from Earth are occurring typically in the mesosphere. All right, then satellites and orbiting of objects are in the thermosphere. By the way, there are an estimated about 6,000 satellites orbiting the Earth, man-made, right? Most of them are communications, some are classified, secret military stuff. Out of those, I think about 4,000 are still working and about 2,000 are decommissioned. So we have about 2,000 satellites that are junk already in the mesosphere, in the thermosphere. Periodically, one of those satellites goes out of orbit, it flies out into space or collapses into the Earth, and we see it make a flash on the pan, as they say, as they burn up. Essentially, they burn up everything, all the components of it just cinch into dust, into smoke. And there was one of them recently that was photographed a week or two ago, and people were wondering, what was that? Was that an asteroid, meteorite, which would have been a natural phenomenon, or was it a satellite, decommissioned satellite that is actually falling into Earth? And I think they established most likely it was a decommissioned satellite that was going through the mesosphere, burning up.
Father, two
Please.
questions if you know.
Yep.
One, which one of these layers is considered quote unquote space? And at what point do things start burning up when they start hitting that level?
Yeah. So for burning as such, you need some oxygen, right? You need some gas to make it burn, all right, as a carburant. And so from the thermosphere down, okay? So I think that inner space is here from the thermosphere up out into the exosphere. Once you go beyond the exosphere or into the exosphere, you're going into outer space. Because I think I've heard that these satellites and orbiting stuff that we have out there is in inner space, okay? So for example, I'm thinking that you can look it up and correct me if I'm wrong, but maybe the Hubble is orbiting in inner space, whereas the Webb definitely is out into the exosphere, is going out into outer space.
Okay, because I know there's like a gravitational limit that they set these satellites on so they won't get pulled down so quickly. And if you set them, they create a stable orbit. But I don't know if that has anything to do with these different.
Right. So the distance,
force.
Yeah, it's a combination of factors, right? So you get the two forces are perpendicular to each other. The gravitational force, which is centripetal, is always pulling toward the Earth, toward the core. All right. So that's one force that is constant, but constant within the layer. So at the surface is that 9.8 meters per second square, you know. But as we go away from the core, it's less and less. So gravity is a weak force generally, weak force, and it gets weaker by the distance from the core, from the nucleus. So out here is a very weak force, but it's still there. Then the perpendicular force is the rockets on the satellite, right? That's why it needs panels. It needs solar panels for an energy source for two things: for the transmission of data that it's doing, right? But also for keeping the jets spurting out and maintaining an acceleration. See, velocity V is a constant speed, right? In a direct line. But to orbit, to make it go around, we actually need acceleration. So if you think about it, again, back to our car, the first love of Americans is the car, right? And the second love is the spouse, right? So if we are in our first love and we are going in a straight line, assuming that the surface of the Earth at a small distance is a straight line, right? We are just at a constant speed. But if we now turn the wheel, we start turning in a circle, even a wide circle. You don't have to burn the tires or anything, make a hard turn. No, even a wide turn, but we had enough room, you know, we had a lot of surface around us, not a road, but a lot of surface, huge surface around us. We started going around, keeping the wheel of the car turned at a constant angle, if you will, of the tires, of the front tires, and started going around describing a circle. We couldn't, if we maintain constant speed, velocity, the car will slow down because of the circle, because of describing a circle. We actually need to press the accelerator slightly to compensate, right? And so for the circular motion, and so we would be accelerating the car, but because we are circling, the circle itself will be constant, all right? The orbit will be a constant orbit, and that's what the satellites do. They have to spurt those jets periodically or constantly at a certain amount to keep the satellite orbiting, as opposed to being sucked in by gravity if they don't accelerate enough, or if they accelerate too much, what's going to happen? They're going to fly out into space. centrifugal force. So the actual motion of the orbit is a vector, right? It's a vector that has two components, the gravitational pull and the thrust of the jets, which are perpendicular to each other at 90 degrees. Okay, so that's just the basic physics behind it. And beyond it, I don't know.
Father Shafi.
Yep.
Just for curiosity, the rockets that had been sent out, are they in the exosphere or in the thermosphere? And how about the
Okay, now
space
rocket,
base? That's what they call it, the space base? Is that what it's called?
space, base.
Yeah, where the astronauts are, that they live there, where are they?
Okay, so you've mentioned several names here. We have to be specific. Okay, a rocket generally is just a container that has propulsion to take out something, to take out either a satellite or an astronaut or both. All right, but the rocket itself is kind of the delivery system. Okay, and rockets typically, once they deploy whatever they're deploying, either a satellite or humans, astronauts, or both together, like in a capsule, you know, then the rockets either fall to Earth and burn up, or some rockets are recoverable, right? Like what was that mission that was launching the? Escapes the name of the mission, escapes to me, but anyway. Some rockets are recoverable, others are not. They burn up on returning when they fall off and have accomplished their mission. So then you're asking about astronauts, for example, the International Space Station, the ISS, right? The largest artifact that humans have made. This is the International Space Station. It's orbiting. I don't know if it's inner orbit or I think it's inner orbit. I think so. Here's the Earth below. These are actual photos of the ISS. Okay, and these are astronauts floating inside the ISS because the gravity is so little, practically negligible for the mass of a human. But for the mass of the ISS, it keeps the ISS going around the Earth. I think it's inner orbit. There's a group of them happily floating in space, but it's inner space. All right. Okay, very, very happy. It's an international, so you got people from different parts of the world, mostly flags, okay. Yes. So Japan, Germany, Deutschland, Canada, US, what is this? Russia. Now the Russians, I heard that the Russians have left the ISS. The Russians have left the ISS because we're at a rock low bottom dialogue or relation with Russia right now because obviously of the Ukraine thing. Okay. So these are in, I think anyone can look it up, but I think they're in inner space, which would be, according to our diagram, the thermosphere. Does that answer the question, more or less? Okay, let's go to the layers. So the upper 10 kilometers, I think I said 100 before, but it's 10 kilometers more or less, 11 kilometers. That's the troposphere. It's a thin layer, really. It's a thin layer. The upper 10 or 11 kilometers, that's where life is occurring, all right? Beyond that, there's nothing living that we know of. It's too thin and too high and too far away from Earth. So the next 40 kilometers, more or less, that's the stratosphere. That's mostly where the boundary for flights, for actual airplanes. Also weather, by the way, you can see this is one of these cumulus clouds, and that's why they're called Strato Cumulus. These huge clouds that form water, the columns. I'm looking at one of them just outside the window here. We get them typically in the tropics and the subtropics. Huge amount of water vapor accumulating until they hit the stratosphere and they flatten out, right? Conditions change, temperature, pressure, etc. And so these clouds, cumulus, it's a reference to column, and strato cumulus because they reach the stratosphere, the lower end of the stratosphere. All right. So most weather occurs within the troposphere, actually. Thin layer, upper 10, 15, 10, 11 kilometers. Beyond the stratosphere is another 40 kilometers more or less. That's the mesosphere. Then another 400 kilometers, more or less, another 400 kilometers, you get the thermosphere. So that inner space, you know, it's a pretty thick one, is 400 out of the 500 kilometers of our inner space. And then you get into, yeah, it's known as atmospheric escape. That's the exosphere, all right? The atmospheric escape. You see the temperature gradient here, how it drops as we go from the troposphere into the stratosphere or the tropopause. Temperature drops to minus 60. It always impresses me when you get into one of those international flights and the airplane goes up into the tropopause, basically, and it's indicating 30,000 feet, right? 30,000 feet is 10,000 meters, which is 10 kilometers. And the temperature is minus 30, minus 40, minus 60 outside the little window that is keeping a pressurized cabin so that we don't freeze to death and blow up because of lack of pressure. So that little thin window is keeping us alive inside the pressurized cabin. All right. And outside that window is minus 30 or minus 60 degrees centigrade. All right. Then we get into the stratosphere. There's a gradual warming precisely because of loss of gas, because of loss of molecules, loss of heat. So the molecules, the gas, the atmosphere is holding heat, right? As we run out of gas molecules, the stratosphere warms drastically into the mesosphere. So the stratopause comes up to about 0 centigrade. This is a centigrade scale, and then drops dramatically into the mesopause. And then as we go into space, of course, there's practically the number of molecules is negligible for heat. And then the temperature rises drastically, especially during the day. And then at night, it will drop drastically, all right? Like the two sides of the moon. I don't know what is causing this drop in temperature here and then this rise between the mesosphere and the thermosphere. Really have no clue. I'm not a meteorologist, but something is going on here that is causing this drastic drop and then rise in temperature, right? And it's the interface of layer between the meso and the thermosphere. But that's why it's called thermosphere, because it warms up drastically, thermally. Okay. We don't have to worry about this too much, other than it's keeping us alive, because a lot of this is deflecting and absorbing ultraviolet radiation, especially A and B, but ultraviolet radiation C, UVC, penetrates all that and hits the surface of the Earth, and that can be cancer causing, all right, that type of radiation. All right. A little more detail about the troposphere and the stratosphere. We see that the bulk of weather occurs precisely in the troposphere. And Mount Everest, one of the highest mountains on Earth, is reaching up close to the stratosphere at the tropopause, at least according to this diagram. All right. Here's the temperature scale. You see the temperature drop and then slowly pick up again. Cirrus clouds, these little plumes that we see on an otherwise clear blue day, right? Sometimes we see the little white scratches on the sky. Those are called cirrus clouds, and they are the basically ice crystals, and they are precisely over there at the tropopause. All right, so those clouds are about 10 kilometers above the surface when we see them, the highest clouds. Here's Strato Cumulus or Cumulonimbus is another name for them. Blue jet, I don't know what that is, some kind of energy. All right, I want to talk about barometric pressure, and then let's see what we have. Yeah, barometric pressure, and then we'll switch gears into radiation. So let's look at barometric pressure. We'll take a break after this. So pressure is a force, okay? And it's called barometric pressure because that's the instrument that measures it. It's called a barometer. Barometer is the instrument that measures, or barometer. It measures this pressure that is downward toward actually the core. The pressure is toward the surface of the Earth. And if it could go beyond the surface, it will go down to the core of the Earth, hypothetically, right? This pressure is caused by what? So we're talking about a pressure that is a downward pressure toward the surface of the Earth. Okay, it's a pressure, so it's a force. If I'm pushing against the wall, I'm putting pressure on the wall, right? So this is a pressure that is being put on the surface of the Earth. This is significant because since we live on the surface of the Earth, and life as we know it lives on the surface of the Earth, we are all subject to that pressure. We're subject to that pressure, but we have been born and evolved within that pressure. And so our bodies literally are pressurized, okay? That's why when we go outside of this pressure system into space, our bodies are not used to being without pressure. And we literally blow out, we explode physically because we don't have the pressure on top of us. Okay, so life is a pressurized life as we know it. When that life goes out of the pressurized system, we explode physically, right? So life is pressurized, but it's normal because everything has evolved. All life that we know on Earth has evolved under this pressure. So the atmosphere has been with us since pretty much the origin of the Earth. What has varied, what has changed is the composition of the atmosphere, all right? This composition has changed over time, but what has not changed basically is to have the atmosphere. So the atmosphere has been with us pretty much more or less since the beginning of the Earth 4.5 billion years ago. But what is causing this downward force? What is causing this pressure? What is causing this pressure is the gas, the gas component of the atmosphere, because gas is not fantasy. Gas is not nothing. Gas is something. It's matter. Gas is matter. They are molecules. They are atoms. And those atoms, mostly because of their protons and their neutrons, which are massive, right? They have a mass, are being pulled by gravity. So gas is also reacting, if you will, to gravity. Slightly, but really. So it is the gravity of Earth that is pulling on the gas molecules of the atmosphere that is maintaining the atmosphere around the Earth as a layer, as a coat. If somehow, let's say that magically we had a switch that could turn off gravity just now, boom, with a push of a button on our cell phones or an app, we turn off gravity. The atmosphere would fly out. The gas would leave. That's not the only thing that would leave, right? The liquid will also fly out, and the solid would also fly out because there's no gravity to hold it in place, to hold it as a ball, all right? So gravity, the atmosphere is held around Earth by gravity. specifically the attraction force of the gas molecules, okay? And that causes a pressure because that gas cannot go beyond the surface. Well, some of it does, kind of seeps in between the cracks of soil and rock and so forth, but that's kind of negligible for the pressure that the atmosphere is exerting on the Earth, okay? And it's a direct influence of the pull of gravity upon that gas. So we live literally a pressurized system. That pressure, because it's real and it's physical, it can be measured. It's empirical, all right? And it's measured in barometric, in the units are atmosphere, 1 atmosphere of pressure. That's at sea level. 1 atmosphere of pressure is at sea level. It's called STP, standard temperature and pressure, right? It's sea level. So in measurement of the barometer, the barometer typically uses Hygonium. Hygonium was the name in Latin. This is Mercury. Mercury. The metal mercury. Mercury is the only metal that we know of on Earth that is liquid at ambient temperature and pressure. Ambient temperature and pressure, all right? The pressure that we have right now, 1 atmosphere, and the temperature that we have right now between 0 and 100 centigrade. Mercury, which is a metal, is liquid. Now, what other metal do you know of that's liquid? No other, copper, nickel, aluminum, iron, these are metals. They're all solid, right? At standard temperature and pressure. But mercury is liquid and it reacts to that pressure slightly. Remember how we said that temperature and or pressure will affect liquids, a fluid. So mercury is thick, but it flows. You have enough mercury, you can pour it. And the magic number is 29.92 inches of mercury in the barometer when it's calibrated to 1 atmosphere pressure. In other words, at sea level. At sea level, barometers are calibrated. The tube has to be thin enough and has to have enough mercury that it would measure from the base out to the edge, right, of the mercury. It will be 29.92 inches, which is interesting because the 29 is inches, but the 0.92 is a decimal of inch. So we got a mixed system here. We got British system of inches, and we got metric system in the decimal, 0.92. All right. Okay, so let's look at a little video that hopefully will allow me to look at the weather, at the barometer, how it works.
One of the great challenges in this book is
you forgot to remind me to go into optimize video clip, and then let's maximize this, and 2 more seconds.
About a subject, to think you're right.
Hello, today we're talking.
Okay. So this young fellow has a barometer on his hand, right? And the mercury is here, but then internally it's going to turn this needle. But there's mercury inside the barometer, which is affected by the temperature and the pressure, the atmospheric pressure. Okay. And so he's going to explain to us in a couple of minutes how this works. You can see, by the way, he's in the fall, going into winter, because the leaves have fallen off the trees. That's a temperate, we can say that this is a temperate forest, by the way, on the biomes.
About understanding barometer readings. And what we use to measure the air pressure is called a barometer. And essentially all air pressure is the downward force of the atmosphere. And when you have more downward force, the air pressure rises. When you have less downward force or less weight, the air pressure drops. And that's important.
Okay, he said a key word, that's weight. So atmospheric pressure, it's also a weight because pressure is a type of force and force is equal to ma, right? Mass times acceleration. That's the general formula. In this case, the mass, the m, is what? The mass of the gas. In other words, the molecular mass of all the atmosphere, of all the gases lumped together, all right? The oxygen, the nitrogen, the trace elements, they all have a mass, right? Because they're atoms, they're molecules. So we add up all that mass and we multiply it times a, the acceleration. What is the acceleration in this case? It's a centripetal force pulling toward the center of the Earth. The A is
Gravity.
gravity, G, small g, 9.8 meters per second square at the surface of the Earth, okay? So the force is that pressure, is the barometric pressure.
Because typically what happens is when the air pressure is rising, the air is sinking, it's putting more pressure on the Earth, but even more importantly, sinking air clears out the skies. So generally you have nice weather.
Right, so again, think about this for a moment. Sinking air has clear skies. Sinking air, there's more pressure, so what it does is it displaces out in that local region, which could be a whole continent, you know, when the atmospheric pressure is high, in other words, that the air is sinking, the atmosphere is sinking into the Earth in that region, the vapor, the water vapor is displaced sideways, all right, like in a circular motion out sideways. And so the sky looks clear because the water vapor is displaced, the clouds are displaced. In another place around the circle of that pressure, you think of it like a column of pressure coming down, around the edge, there's a greater accumulation of weather, it's a greater accumulation of vapor or cloud formation, and then there is less pressure there, so that weather is going to rise and clouds rise, you know, with less pressure. And that's the beginning of the cycle that we're going to be talking about that makes the weather.
When the skies are clear and the barometric pressure is high. When the barometric pressure falls, you have rising air. It's rising away from the surface of the Earth, so the pressure that it's putting on the Earth goes down, the pressure falls. And typically with low pressure, you have clouds, you have rain.
Why do we have clouds with low pressure? Because now low pressure rises and is sucking in from the sides the humidity that is around, the water vapor that's around, or the clouds that are around the side get sucked into the center where we are in a low pressure as that atmosphere rises.
Rain, and when you have extreme conditions, you can also have thunderstorms, sometimes severe. The lower the pressure drops, you also get the worst weather. For instance, the lower the pressure in a hurricane, the stronger the hurricane is. So understanding how to measure it, we use these barometers. And it's very simple to read a barometer to tell you if the weather's going to turn good or bad, or whether you have high pressure or low pressure. Standard pressure, kind of the average pressure, is 29.92 inches of mercury. That's the way.
That's the magic number, 29.92 inches of mercury.
We measure it, that's the way it's marked out on most barometer, whether it's a mercury barometer, a water barometer, or an aneroid barometer. This type is an aneroid barometer, but when the pressure rises, the needle goes up, and if you measure...
Sorry, my bad, I thought it was a mercury barometer. This is actually a mirror, but it's an aneroid barometer, meaning it's a coil. It's a coil that stretches or compresses with pressure, and that coil makes the needle go around.
Against 29.92, anything above 29.92 is considered high. The closer you get to 30 or 31 is considered high. And the farther below 29.92 you go, the closer to 29 or even below 29, that means the pressure is low. So simply watch it and gauge it against that 29.92 inches of mercury. Above it is high, below it generally is considered low.
Right.
Ready to start eating healthy?
Okay, so high pressure is good weather, right? Kind of counterintuitive, right? High pressure, good weather, low pressure, bad weather. And it may just be 1 or 2 inches of difference from the 2992. You can think of almost 30. Above 30, good weather, below 30, bad weather. Inches of mercury, okay? And that 2992 is 1 atmosphere. So 1.1 is more pressure, right? Bad weather. Less than 1 atmosphere pressure, what we want is good weather. Sorry, backwards. Higher, 1.1 would be good weather, high pressure. Low pressure, less than 1 atmosphere is bad weather. It's sucking in from the sides. Questions? People got it? All right. Ready for a break? I'm ready. Okay, so it's 11:22. I'm going to start at 11:30. All right, start at 11:30. If there are no questions or comments, we'll take a little break now. I'll leave the next slide on here and pause recording. Pause recording. Okay, 11:30. So welcome back into the second half of today's lecture. Now, I want to shift gears a little bit and look at the distance between the Earth and the Sun so that we continue to explore these proportions and relations, right? Ratios, proportions, and relations with regards to distance and what is actually heating or cooling the surface of the Earth and why some places are colder than others. First, let's start with the ratio of the diameter of Earth to the diameter of the Sun. The ratio is about 100 to 1. In other words, the diameter of the Sun, which is represented at the extreme of this slide here, right? The diameter of the Sun is a line, the diameter of a circle is a line that goes from one edge of the circle to another, passing through the center. Okay, that's the diameter. It's twice the radius. The diameter of the Sun is about 100 times the diameter of the Earth. So here I have them to scale. The red Sun, should have made it more yellow maybe. And the Sun is dying out. And the blue Earth here, okay, this little blue dot, that's more or less the ratio. So if we take this blue dot, we would be able to fit 100 blue dots from edge to edge here. That's the ratio. Now the distance from the Earth to the Sun, the distance in Earth units is about 10,000. In other words, we are about 10,000 Earth diameters from the Sun. Okay, so is this little diagram to scale? It's only to scale with regards to the diameters of the Earth and the Sun, but it's obviously not to scale with regards to the distance from the Earth to the Sun. Again, if we were at this distance to the Sun, we would just melt and evaporate, will boil. The Sun will, the Earth would boil, okay? And probably just collapse into the Sun by gravitational pull. If this is actually, I figured it out the other day. So here we are at St. Thomas University, the College of Science, the actual building of science, is close to 32nd Avenue, right? 32nd Avenue. And the main entrance is over there at 37th Avenue. So the actual distance from the Earth to the Sun to scale, all right, for those of you who have been at St. Thomas campus, if the sun were about this size of a ball, if the sun were about this size of a ball, the Earth would be over there at the entrance gate. All right, the Earth would be at the entrance gate, just to put it to scale. In other words, about 5 blocks away. What I'm trying to say is that if we were to make this diagram true to scale for distance to the sun, this little blue dot would have to be 5 blocks away from this red ball to put it to scale. That's our distance to the sun to scale. All right, so it gives us a feeling for how distant we are. In fact, the light from the sun, anybody know how long it takes from the sunlight to hit Earth, to actually arrive on Earth?
8 minutes.
Yes, thank you very much. 8 minutes, exactly. 8 minutes. That's traveling at what? At sea, which is 300,000 kilometers per second. All right. So you can figure out the distance. You can figure out our distance. You take 300,000 times 60, makes 1 minute, times 8 makes the 8 minutes. All right. So 300,000 times 60 times 8, that's our distance from the Earth to the sun. From here, beyond the gate. Yeah, okay. Therefore, it's not really the heat of the sun that is warming us up, but rather the internal heat of the Earth. It's a point I made earlier with regards to the geosphere. But the surface is heated somewhat by the rays, by the how much atmosphere the ray has to go through, the ray of light, okay? That has to do with refraction, which is the bouncing of the ray, of the light ray, on the surface of the Earth. Because what we have is when there's a transformation of energy from light to heat. In other words, when light heats a surface, some of that light is reflected to the eyeball, for example, so that we can see the light, right, on the surface of an object. But some of that light energy is also transformed into heat. So you can say that literally there is some loss of light because of the generation of heat. Some of that light becomes heat energy, which is then radiates out and it's lost, okay? It's lost. That's why the old incandescent bulbs, I mean, I'm so old that I remember incandescent bulbs, right? And some of you still remember incandescent bulbs. They had the ones that had the filament inside, they became quite hot, right? So hot. So all that heat was loss of energy. So the light, the white light, the photons that we got from that bulb was not very efficient. We were getting light out of it, but we were also losing a lot of energy. A lot of electrical energy was wasted in the heat of the bulb. And that's why burn your fingers when you try to change those bulbs. When they went out, they stayed hot for a while. All that heat that was radiated out was lost energy. Eventually goes out into space. It forms what we call entropy. Entropy, which is energy in space that is unavailable for work. So it's lost. And that's why it's called chaos, or, we're going toward a cooling effect. Anyway, back to the sun and the Earth and the light rays. So these light rays are represented here in parallel. What I'm trying to say is that two things. First of all, the surface of the sun is 100 times bigger than the Earth, right? Therefore, for all practical purposes, sorry, I had skipped a slide. For all practical purposes, no, let me go back here for a moment. The sun rays that are hitting the earth, okay, for all practical purposes, those sun rays are coming parallel to each other. So you can kind of think more or less, because the surface of the earth is so much bigger than the surface of the sun, is so much bigger than the earth, the light rays of the sun that are actually hitting the earth, practically they're coming in parallel, almost like from a flashlight, all right? From a flashlight that generates more or less a cylinder of light going forward, okay? That's simply because practically the surface of the earth for us, for the surface of the sun for us, is practically flat. It's so huge that it's practically flat. It's something similar, analogous to us being on the surface of the earth. The surface of the earth itself, in scale to the human body, to 6 feet, I mean, 6 feet is a tall person, right? In scale to 6 feet of the human body, and our eyes are toward the top of our height, right on the head, the surface is so huge. The surface of the earth is so huge compared to the scale of a human that for all practical purposes, it looks flat. It doesn't look curved, all right, when we look at the horizon. But in fact, we know that it is curved. Otherwise, when we take photos of the earth from space, we wouldn't see a circle, we wouldn't see a disk, right? If it weren't circular, if it weren't a sphere. But it is a sphere. And so, but it looks, to scale, it looks flat, all right? That's kind of similar. The surface of the sun is so much bigger than the surface of the earth that for all practical purposes, the sun rays that are leaving the sun and hitting the earth are essentially parallel to each other. It's like a cylinder of light from a flashlight, all right? So we know that the light radiates from the sun, just like heat radiates or gravity radiates from the earth, all right? It's just that the rays that are coming out above the earth are not hitting the earth. And the rays that are coming out below the earth are not hitting the earth either. So we're only concerned with this little circle of light that is leaving the sun that is hitting the earth. Because light that is coming out of the sun above here and below here on the other side of the is not hitting us. It's not, only a very tiny little fragment of light from the sun is hitting the earth. Okay, so that's the first thing. Those rays, practically the distance is so long and the surface is so huge that they're practically coming in parallel. Now, we can look at what is called the angle of incidence, all right? The angle of incidence. If we were to trace an imaginary tangent, a tangent is a straight line that touches the perimeter of a circle, all right, what is called the circumference, at only one point. So think of a circle, a quarter, you know, or a silver dollar if you want. And the periphery of that circle is the perimeter, is the circumference, right? The circumference is made up of any number of points, really an infinite number of points, because we can always have a smaller point between two other points. It's a mathematical thing, no, a point. A tangent then is a line or a plane. Well, let's stick with the two surfaces for now. It's a line that touches the circumference only at one point, okay? If it touches not at one point, but are 2 points, it's no longer a tangent. What is it called? It's called a secant, right? Now it's slicing through the circle at 2 or more, at 2 points, right? That's called a secant, it's not a tangent. But a tangent only touches at 1 point. Also, therefore, by definition, a tangent is always perpendicular to a radius, or a diameter traced from that point inward, because the radius is from the center of the circle to a point on the circle, on the periphery, right? So if a tangent is touching that one point, that tangent is perpendicular, 90 degrees from the radius, and therefore also 90 degrees to a diameter, which will be 2 radii, going through the center of the circle. Okay, so that's a tangent. The angle of incidence is the angle that is made, that is generated between the tangent and the sun ray. The sun ray, okay? So actually I should have this A3 way down here at the equator. At the equator, the angle, so at the equator, the sun ray is hitting that equator at 90 degrees to a tangent. We had a tangent of the equator. Now think of, okay, we have to make it 3-dimensional because the Earth is not a circle, it's a sphere. So the tangent, instead of being a line, is now a disk, right? It's a disk. It's a disk on a sphere. Think of the old LP records. Some of us remember LP records, long playing records, right? The old flat records on the surface of a basketball, right? Take it to the equator. And so we have this disk here, flat, vertical, on the equator of a basketball, and the flashlight is shining. So the angle of incidence at the equator is going to be what? The angle of incidence at the equator is going to be 90 degrees, because that disk is vertical and the rays are coming in horizontal. And so they're perpendicular to each other. So that's 90 degrees angle of incidence. Okay. Now, move that LP disk toward the top of the basketball, but you keep the flashlight coming in parallel, all right? Keep the flashlight rays coming in at the same horizontal plane. You notice that the angle of incidence is becoming greater and greater, okay? So this angle of incidence is going to be a little bit more than 90 degrees. This one more than 90 degrees, and this one more than 90 degrees. Actually, the angle of incidence is on the inside. It's on the inside here. The angle of incidence is the converse. It's on the inside. So as we move away from the equator toward the pole, the angle of incidence gets smaller and smaller and smaller, all right? Until finally the rays at the poles is practically zero. The angle of incidence is practically zero, okay? All that to say that the sun rays are more concentrated on the equator and more dissipated on the poles or near the poles, because they're covering the same amount of ray, the same amount of intensity of energy, of photons, of light energy, is covering more surface toward the poles and less surface toward the equators. This one is a little more illustrative. See, the area is smaller, the surface is smaller, and the area is larger, smaller toward the equator, even though the equator, so we have to tilt the Earth. Okay, we know that the Earth is tilted. We have to untilt it to make it the equator, right? But it doesn't matter. There's still a hypothetical equator here, horizontally on the Earth, and less area is being covered by those rays, sun rays. As we move toward the poles, more area is covered for the same amount of rays, Therefore, when we look at the transformation of energy from light into heat, right? There's more intensity here because there's less area, less surface, receiving the same amount of light. So when some of that light converts into heat, there's going to be, the net result is there's going to be more heat at the equators and less heat per surface toward the poles. And that's why the poles are colder than the equator. Okay, has to do now. It doesn't have to do, excuse me, let me finish the argument. This is different from the overall temperature of the crust, which allows for liquid water, okay? That temperature is being generated from the core out, heat dissipation. That's different. I'm not talking about that heat. That heat is more or less a constant heat on the crust of the Earth throughout the whole orange, throughout the whole basketball, all right? This is different. This is heat on the surface coming from outside the system, from outside the Earth, coming from the sun, from another system. And this is heat that is a transformation from light. So when we shine light on an object, some of that light bounces off, reflects, hits our eyeballs, and we can see the object. But some of that light, a little bit of that light, is also being transformed into heat. So literally the object is warming up a little bit by shining light on it. Very tiny amount, but real. And that makes the difference in temperature between the equator, the tropics, and the cold regions of the two poles, all right? In between, what do we get in between? We get temperate. So we go from warm tropical rainforest to cold winter taiga or evergreen forest, coniferous forest. And in between is where we have the seasons, the 4 seasons, that is temperate. And then it varies according to the orbit of the Earth, the elliptical orbit, the 4 seasons. That one does vary according to the distance to the sun, because the orbit is elliptical. In a year's time, it's not circular, but it's an elliptical orbit. So in the summer, we're closer to the Earth, and in winter, we're further away. Spring and fall, we're equidistant, kind of halfway on the ellipse. Okay, questions, comments?
No, it's okay, Father. I got it. Thank you.
Okay. Okay. All right. So it's a little tricky. There are several systems that are here, several things that need to be understood. First, the very thing is that the sun rays are hitting the Earth essentially parallel. So we have more or less the same quantity of light hitting the poles or the equator or anywhere on the surface of the Earth. Okay, but because of the angle of incidence, there's more area with the same amount of light covered toward the equator, toward the poles, and less area toward the equator. So another way of saying that is that the sun rays are more concentrated around the equator and more dissipated around the poles, all right? Also, they have to go through more atmosphere going in the poles and less atmosphere going to the equator. And so that makes a temperature difference when those rays, light turns into heat. Okay, so what we're doing here is we're building the case for weather, for the weather patterns, seasonal weather within a year. You know, the 4 seasons, which don't really occur in the equator. In the equator, we have rainy season and less rain, but generally the same amount of hot weather. In the poles, we have the opposite. We have generally very cold and essentially water as ice, all right? And then in between, we get the temperate regions, but there's a gradient. And that gradient, again, you guessed it, is another type of complex system. That is the weather patterns. Now, we have to look at another type of cycling that is called Coriolis effect. because this phenomenon was discovered by this Coriolis guy. So he got the last name put into the effect to this day. All right. So the Coriolis effect, it has to do with a couple of forces turning. First, we have already the convection currents that we understood last lecture, the convection, that is cold air sinks, but it cannot sink beyond the surface of the earth, right? So now it has to travel along the sphere, and it's going to travel downward toward the equator in the northern hemisphere. It's going to travel upward toward the equator in the southern hemisphere, and in the equator, it's going to find warmth, right? So that air is going to warm up gradually as it warms. Because it's a fluid, it's going to rise into the atmosphere, right? This is the troposphere, basically. It's going to rise toward the stratosphere at the equators, right? That's because of the convection current. As it goes high, 10 kilometers, 11 kilometers, and it starts hitting the stratosphere, there's a gradual dropping of temperature, right? So it cools. And so as it cools, it's going to be moving toward the poles again, and then sink again and have that circular motion. That's just convection currents on the fluid of the atmosphere, of the gas atmosphere, of the actual molecule, the gas molecules. That convection current is kept around the Earth by gravity that is pulling on those molecules, okay? But in addition to that, the Earth is also spinning because we just couldn't stay still, right? We got to spin, and we got to do two spins. We got to spin around our own axis. I'm talking about the Earth. And then we got to spin around the sun also. Then there will be another story about the sun, the actual planetary system spinning within the Milky Way. But that's a different story. For our purposes, we have this double spin. We have the spin of ourselves, of the Earth rotating around its own axis, which is beginning to wobble, by the way. The more it wobbles, the more eventually will fly out into space or collapse into the sun because it's going to lose its balance, orbital balance, okay? So that's the first spin. And the second spin is going around describing an ellipse around the sun, which is going to generate the seasons, the 4 seasons. So the spin is going to make the air around us, the atmosphere, also spin. And that's why we don't feel a drag as we go through space, you know, as we orbit around the sun, we don't feel a drag, okay? Because the atmosphere stays with us and it's also spinning with us. And we don't feel the spin of the Earth, but you take away the atmosphere and we'd be flown out of the Earth because of the spin of the Earth. What's the fastest thing on Earth? Earth itself, the spin of the Earth, okay? Which, by the way, is fastest at the equator, because that's the greatest distance from the axis, and is, we can say, if we are at the actual pole, not the magnetic pole, but the geographic pole center of the axis, the spin is negligible because it's basically at the, you know, we're at the tip of the top spinning, or the tip of the bottom spinning, okay? Okay.
Father Trophy, I'm sorry, I'm going to ask a question that may be very dumb, but I'm a little bit confused about this.
Cristina, can you switch microphones into the other one that we can hear better? Appreciate it. So otherwise it's just too muffled.
I will ask you later.
Okay, if you can do that, I appreciate it because it's hard to hear. Okay. All right. So now what we need to add to the convection currents that are occurring in the atmosphere, the fluid of the atmosphere of the gas, is the spin of the Earth. Okay. And that spin is going to cause what is known as an angular momentum. And the overall effect is this Coriolis effect, which is an angular momentum, so that the weather on the atmosphere is going to rotate in this funny fashion of curvature, all right? So here is a little site that we can look at. How can I rescue this? Give me a minute to rescue. Okay, let's look it up. The Coriolis effect. So let me just go here for a moment. It's this one. All right, I'm still on the, give me a minute. Go here. Optimize, yes. Okay.
If you've ever
Stop. All right, a little bigger. Yeah. Okay. It's just a 3-minute little video explaining the Coriolis effect and angular momentum. Angular momentum, which has to do with rotation in place. Rotation in place. Think of a top. Remember the tops? I used to play with the top when I was a kid. Yes, from last century. They would spin on a point until the top started losing momentum, which is angular movement, rotation around an axis. And eventually the top will start wobbling and then fall off, right? Fall and stop. What was causing the top to stop? The rotation. Believe it or not, friction. Its surface against the air around it, the local air, because it's a fluid, was offering resistance. And at the microscopic level, the little particles that made up the surface of the top, right, of the spinning top, was causing friction with the atmosphere around it. It's like sticking your hand out again on the car at 55 miles an hour, pull down the window and stick your hand out. You're going to feel air drag, and that hand outside the window is going to slow down the car a fraction of speed because it's causing friction, right? Okay, so that made the stop. But the Earth, because beyond the atmosphere there's no friction because it's space, then it keeps rotating and it doesn't stop.
ever watched the news during a hurricane
An
or
aside.
wintertime north?
Oh, sorry. Yeah,
Okay.
just a quick aside for the old folks. There's also friction at the very tip of the tops. So
Yes.
what you would try to do is sharpen it as much as possible to keep it spinning.
Yeah, right. So the ideal spinning was a very sharp tip of the top on glass, right? On a glass surface or ceramic or the floor.
Slide on the surface.
The living room floor with tiles. Yeah, probably that friction was even more significant than the air friction. Thank you.
If you've ever watched the news during a hurricane or wintertime nor'easter, you've probably noticed that big storms spin over time as they travel. In the northern hemisphere, they spin counterclockwise. But if you were watching a storm in the southern hemisphere, you'd see it spinning clockwise. Why do storms spin in different directions depending on their location? And why do they spin in the first place? A storm's rotation is due to something called the Coriolis Effect, which is a phenomenon that causes fluids like water and air to curve as they travel across or above Earth's surface. Here's the basic idea. Earth is constantly spinning around its axis from west to east. But because Earth is a sphere and wider in the middle, points on the equator are actually spinning faster around the axis than points near the poles. So imagine you were standing in Texas and had a magic paper airplane that could travel hundreds of miles. If you threw your airplane directly northward, you might think it would land straight north, maybe somewhere in Nebraska. But Texas is actually spinning around Earth's axis faster than Nebraska is, because it's closer to the equator. That means that the paper airplane is spinning faster as well. And when you throw it, that spinning momentum is conserved. So if you threw your paper airplane in...
Sorry, the key word here is conserved. Conserved spinning momentum, right? The spinning momentum. So the paper airplane takes off at a faster speed, right? And it's going to try to conserve that momentum, conserve spinning momentum, but now it's going to start rotating.
In a straight line toward the north, it would land somewhere to the right of Nebraska, maybe in Delaware. So from your point of view in Texas, the plane would have taken a curved path to the right. The opposite would happen in the southern hemisphere. An object traveling from the equator to the south would get deflected to the left. So what does this have to do with hurricane spinning? Well, at the center of every hurricane is an area of very low pressure. As a result, the high-pressure air surrounding the center, or eye, of a storm is constantly rushing toward the low-pressure void in the middle. But because of the Coriolis effect, the air rushing toward the center is deflected off course. In the northern hemisphere, the volumes of air on all sides of the eye keep getting tugged slightly to the right. The air keeps trying to make its way to the middle and keeps getting deflected, causing the entire system to spin in a counterclockwise direction. In the southern hemisphere, where the Coriolis effect pulls air to the left, the opposite happens. Storms spin around the eye in a clockwise manner.
Okay,
If you've ever watched the news during a hurricane,
we got it. All right, so you see, that causes a pattern not only of drastic weather like hurricanes, but even normal weather, like the rainfall or no rainfall, and the weather pattern on the surface of the earth, right? Is that Coriolis effect. And so we end up with basically 4 bands. You know, there's the equatorial area, low because of high pressure, right? The air, low pressure because the air is rising. Then we have subtropical trade winds, westerlies, and then we get into subpolar and finally polar high. So we have all these, and they are more or less at 30 degrees from each other. On these 30 degrees, it's not a temperature now, this is degrees angle from the center. So 30 degrees latitude, north or south, 60 degrees, or 90 degrees latitude, north or south, which is the poles. Okay. Now, yep.
Can you hear me now?
Yeah, but let me raise my volume here. Okay, go ahead.
Okay. I'm just a little confused, but I think
okay.
So the convection currents that we're talking, there are some that occur because of the heat from the core, right? That comes from the center of the earth.
No.
The ones we're talking about.
No.
No.
Hold on.
Okay.
We have convection current. Convection current is a phenomenon of fluids, right? As they dissipate heat, it makes them move, it makes them rotate. That's the convection current. Now, there's convection current that we saw last class, which was at the mantle, right? The mantle, which is halfway or below the crust and above the core, right? That's the mantle. The red hot magma lava stuff is fluid, it's a thick liquid, magma, lava. Those have convection currents. And that's turning and that's making the crust shift a little bit, what we call continental drift, right? Plate tectonics. That's a convection current just by itself. The same phenomenon also occurs in the atmosphere with the air. That's convection current. Sinking in the poles because it's cold air. That cold air has nowhere to go but to the equator, dropping down from the north or coming up from the south, right? That air on the surface of the earth can only move toward the equator. At the equator, that air is getting warmed up but not because of the core. This warming up is external heat. This is the heat that is produced by some light turning into heat. So it's a different source of heat.
That's
The
what I wanted
phenomenon
to-
is the same. The phenomenon is a convection. But on top of that convection current, we also have to add the spin of the Earth, which is going to make that pattern now rotate in this other type of pattern.
I understand that now.
Okay.
And just for curiosity, they never met. Those two, there's no phenomenon where from the center of the Earth, from the atmosphere, something could happen.
Again, the question?
So like that you could have an earthquake and a hurricane, something similar happening because of the heat coming from the center of the Earth and the atmosphere. That doesn't do anything. They never met. They
Right.
never have. Thank you, Father, but I understood. Thank you.
Okay, okay. If anything, okay, so we can ask, maybe asking your question in a little different way. What is the contribution? Is there any contribution of the heat of the Earth to the atmosphere? All right, as opposed to the sunlight heat. What is the contribution? What might be the contribution of the Earth's own heat to the atmosphere? And there is a contribution, okay? But it's a more homogeneous contribution because in principle, the internal heat of the Earth, because it is a sphere, is more or less uniform. See, so the internal heat, think of the core, white hot, think of the magma, red hot, is more or less homogeneous, being applied, if you will, to the crust, to the inside of the crust. So the Earth is being heated up, let's say, by its internal heat, more or less homogeneously. The crust is kept warm, if you will, all right, more or less homogeneously around the entire globe. That does have an effect on the atmosphere in keeping the atmosphere in principle, or before we add the external heat, before we add the heat of the sunlight, the atmosphere would be pretty much homogeneous heat, right? Would be heated up homogeneously, okay? That's kind of in the big picture. And the range is going to be precisely that range of temperature that it's a little cooler than liquid, so that the atmosphere, the water in the atmosphere stays a little warmer, so the atmosphere stays at water vapor. But in fact, we don't have just the internal heat of the Earth. We also have the external heat of the sun rays converted into heat. And that has a more direct impact on the weather system, has a more direct impact, okay? Because since it's the surface of the Earth that is getting heated up, specifically the outer part of the crust, literally the surface of the crust, right? The outer surface, then that has a more direct impact on our weather. But there is some effect of just by the fact that the globe itself, the Earth itself, has its own temperature, like the crust has its own temperature that is being maintained by the core. All right, so this pattern then, this Coriolis effect, has to do with what the lady mentioned, the conserved spinning momentum, okay? But she didn't really explain that. She did explain it kind of sideways, saying that the equator rotates faster than the poles, all right? And again, that is this thing called conserved spinning momentum, all right? And so we can think of an ice skater that gets on the tippy toe of one skate. First, she has her arms out and maybe a leg out also. and that she's going to have a particular momentum, which is a circular speed. But if she pulls in her arms and her leg, the speed increases. All right, the spin increases, she goes faster because there's now more mass, literally more mass toward the axis, toward the center of the body. Whereas when her arms are stretched out and her legs stretched out, then the mass is more dispersed toward a perimeter. Okay, so the body as a whole, the momentum slows down. Okay, or the speed slows down to conserve the momentum precisely. And that result has to be the same. Okay, so here's another little video of the conserved spinning momentum. No, wrong. Hold on. Oh, okay. Sorry. So that's the same video. Why is this different? Oh, okay. Yes. Sorry. When I went to look at this video last night, actually, this is disabled. It became private. So this was not available. So instead, I had this one, which is the one we just saw, that explains the angular momentum and how the speed is faster at the equator because there's a greater radius, radius and a perimeter than the poles. All right, bottom line. When we put all that motion together, the convection current illustrated by the red and blue arrows, that's convection, all right, which is kind of up and down of the atmosphere in relation to the surface of the Earth. And we add the Coriolis effect, the spinning effect, represented by the horizontal arrows here. You can think of them as kind of horizontal flat on the surface of the Earth because of the spinning. We get the weather pattern, what is called Hadley cells. Hadley cell, because another guy who discovered them, his last name was Hadley. Okay, so this was some kind of a meteorologist who discovered this pattern, Hadley cells. Bottom line, there are these 6 Hadley cells, all right, 3 in each hemisphere. So the northern hemisphere, Hadley cells, and the southern hemisphere, Hadley cells. There's one that spans from the tropics. Let's say we start from the tropics going north to the North Pole, right? The first one start at the tropics and will go about 30 degrees north, latitude north, to the subtropical region. And this is the first Hadley cell, right? The tropic, subtropic Hadley cell, which is generally warm winds and warm weather pattern. Then we have from 30 degrees to 60 degrees latitude north, we have the second global Hadley cell. They go all around the globe, all right? And that one is temperate. And that one generally covers North America and Africa, Europe, and the northern half of Asia, let's say globally, what would be Central Asia, most of China, Mongolia, etc. Right? That's temperate. This is the area that generally has the 4 seasons, more or less even, of 3 months each of the 4 seasons. So it's the greatest variation in temperature is going to be in the temperate region, either north or south. It's just that in the south, there's less continents, right? You got the southern half of South America and Africa, and then the southern part of Asia. But in the northern hemisphere, you have more continent, more landmass. Then finally, when we get from 60 degrees to 90 degrees latitude north, or south, we have the subpolar, either subarctic or subantarctic in the southern hemisphere, all right? And that's the coldest weather pattern. It's called the polar easterlies, all right? And that's the coldest weather pattern. And it generally stays cold with freezing temperatures. So there is, again, little precipitation because there's no condensation. But you get the most weather pattern of what we normally call weather in the interfaces, okay? Especially the interface between the temperate and the north and between the two tropics here, because this is the largest accumulation of water vapor. You see, notice that these Hadley cells between the subtropic and the temperate are moving in opposite direction. In other words, this convection current is going this way, right? If we look at it straight on, it's going clockwise, whereas the temperate Hadley cell is going counterclockwise, all right? And so both of these cells are contributing cold air down into the 30-degree latitude to be warmed, either going south or going north. And so then that's going to turn into water vapor that is being supplied either at the equatorial region or at the interface between temperate and polar region. Okay, and that's why it's mostly cloudy and rainy around Seattle and that area and Canada in general. All right, it's going to be cloudy and rainy. And also Siberia on the European side and the Asiatic side. In the southern hemisphere, that coincides mostly with the lower Pacific Ocean. So there's very little landmass down there, mostly the southern tip of South America. But the ones that affect the weather most in the northern hemisphere is this subtropical Hadley cell, and most especially the temperate Hadley cell, all right? So US and most of Canada and Europe and most of Northern Asia is immersed into this temperate Hadley cell. And that's why the weather generally is kind of benevolent. The 4 seasons, more or less, warm or cold by each year, depending on some other phenomena that happens mostly on the Pacific Ocean. And these two phenomena are called El Nino or La Nina, which is just based because a reference to El Nino is a reference to the child Jesus. In other words, around December 25th, 8 on December, in other words, the winter, the beginning of winter, or the winter season. Okay, El Nino is the birth of Christ. And so that creates a weather pattern that can affect the global weather, especially in the northern hemisphere. And then the opposite of that weather pattern is La Nina, which is, the female, the opposite of the male. So I just read recently in so El Nino causes generally more wet pattern, more wetter pattern of weather in the northern hemisphere. So La Nina causes a drier pattern, okay, the opposite. And I just read recently in the BBC just last week that for 3 years in a row, which is very rare, for 3 years in a row, we've had La Nina weather pattern, all right, a phenomenon for 3 years in a row. And that's why for 3 years in a row, it's made it extremely dry, especially during the summer time. It's been extremely light, low rain, and therefore all this desiccation, all this desertic droughts that the earth has been experiencing for the past 3 summers. But more dramatic weather in general, more dramatic. So the summers are hotter, drier, and then the fall, spring and fall are wetter and colder and more dramatic weather. fluctuation, okay? Because 3 years in a row of La Nina weather. So those are long-term weather patterns that are beginning to push toward eventually what could be climate. And so that leads me to the next to the last slide, which is the difference between weather and climate. But before I leave weather, questions, I mean, this is very basic, really. It's kind of weather less than 101, okay? This is weather 99 or something like that. Just the basic weather patterns. When we get up to the level of the Hadley cell, which is a complex flow between convection currents and Coriolis effect of the spinning of the Earth, right? That is beginning to approach the realistic weather patterns of the year, of the seasons, from one year to the next, okay? And it all has to do with these Hadley cells, the way they move in the troposphere, okay? So from there, we finally can talk now about weather and climate, beginning to talk about it. And this is a drastic photograph. It's an actual photograph of somewhere in the world with the little city lights down here in a very pitch dark night and lightning discharge, which is, by the way, friction. That's another one. I've talked about friction tangentially, but friction is a type of static energy, therefore electrical energy, static electrical energy. You know, at night, especially when it's winter time or when you have your temperature setting, your thermometer, what was that called? The AC setting like at 65 degrees, you know, your walls are sweating at night, and you take the sheets, the bed sheets, and you go like that and you shake it in the dark and you see little sparks, right? And sometimes it happens to me. I mean, actually, it's been happening to me in the winter time, especially if the church has a rug, right? Has carpeting, or if the people are wearing lots of winter clothing, warm, fuzzy clothing, they generate static electricity. And sometimes when I give the hose, I get a little shock. I get a little spark on the finger. Body of Christ, ouch. Your tongue just shocked my finger. But those little sparks is a miniature micro version of a lightning. In other words, the Hadley cells, as the air gas is rubbing against the surface of the Earth, it is generating static electricity that is building up inside the Hadley cell, okay, until that buildup can't take it anymore. And I forget if the cloud is negative and the Earth is positive or vice versa, but there's a charge differential between the two. And that atmosphere becomes so charged, literally, with static energy, you know, potential energy, that it can't stand it anymore and releases the charge by way of a lightning, okay? Because the lightning is a very fast release of electrons that are flowing through mostly water vapor in the atmosphere. It flows so fast that it generates a shock wave that is sound, and that's the thunder. But sound needs a medium to travel through, and the medium is literally the atmosphere, the molecules of gas in the atmosphere. That's what transmits the thunder sound shock wave, right? Whereas light photons traveling through don't need a medium to travel through. That's why we can see the sun and we don't hear the sun, including nuclear explosions that are occurring on its surface, because light photon, unlike sound, doesn't need a medium which to travel. Bottom line, we see the lightning before we hear the thunder. And if you count in seconds, that is supposed to give you an approximation on how far away that lightning struck, all right? Between the time that it takes between you see the lightning and you hear the thunder, it's supposed to be more or less in miles, a mile per second. It's very approximate, okay? But if you see the lightning and you start counting, The Mississippi's 101, 102, or 1 Mississippi, 2 Mississippi for flag football. At 5 Mississippi's, you hear the thunder. Supposedly the lightning fell 5 miles away. Give or take marginal error of about 5 miles. So it could have been hitting right on top of you or 10 miles away. It's a very rough estimate, but the longer the time between the lightning and the thunder, the further away in general the lightning struck, okay? Another phenomenon is in the middle of a hurricane where you actually see the lightning, or I saw the lightning at where Andrew in 1995 was coming through, 1993, when the hurricane was coming through in the middle of the night, pitch dark. I could see the flash of lightning, but I couldn't hear anything because the howl of the hurricane, which was louder than the thunder of the lightning. Okay. All right. 12:30. Questions, comments? We just kind of scratch the surface on the atmosphere, mostly concentrating on the troposphere, which is where life occurs, and the various phenomenon there of weather. Oh yeah, okay, so back to the punchline. Weather is happening all the time on a daily basis. There's a weather difference between day and night, right? Literally, light, no light, which also comes with it generally a lowering of the temperature of the atmospheric temperature at night because there's less light that is being transformed into heat, etc. Okay, so weather patterns change all the time. They change daily, they change by the hour, they change every minute. It's a dynamic system that changes a lot. So we can say that weather changes by the hour. 1 hour it's sunshine, the next hour is raining, okay? By the day, by the week, the weather pattern for the week, right? By the season, so within a year, it also changes from summer to winter, etc., from very warm to very cold. So weather pattern is changing dynamically all the time, very dynamic. Over a long period of time, you start adding up weather patterns year after year after year after year, into centuries, into millennia. You start going into climate, all right? You start going into climate. The climate time scale is typically in the thousands and more comfortably into the hundreds of thousands of years. So to talk about climate change is an approximation. It's an approximation, okay? We'll get into more details later after we cover cycles, water. We have to look at the hydrosphere before we get into cycles. And then finally, after cycles, in the context of population growth, human population, we'll look in more detail at climate and climate change. All right. And here is just a
Father,
mm-hmm.
Father, it's Frank Kelly here.
Mm-hmm.
We were speaking earlier about the atmosphere with the gas, every kind of the component of that we have. I'm speaking about what I am living now, especially in my country.
Yes.
With
yes.
The effect of the everyday, that the burning of the tires.
Yes.
That how that can affect that this kind of the gas, natural
yes.
gas, that risk of all the gases that we have in the systems.
Yes.
How that can affect with the
yes.
kind of the oxygen of the respiration of the human being.
Of course, it's overall it's a negative effect. Okay, so let me give a little bit of background because Father Franco, one of our students, is now in Haiti. All right, and what we have is a drastic situation, as in some parts of the world. He has just described what is being reported in the news. All right, that there is unrest, there is a lot of civil unrest. Sadly, for many years, there has been corruption in the official government and so forth. And so it's a very drastic situation. He was referring specifically to the burning of tires as part of the civil unrest. Now, the tire itself, if we look at it chemically, we know that it's made out of rubber, which is, it's mostly comes from fossil fuel, all right? And it has some plant material in there, but also, so rubber has a lot of fossil fuel in it. And when it burns, it produces a lot of CO2, smoke that we're seeing here, and that goes into the atmosphere, right? Now, a lot of this is staying locally, is not really affecting much the global pattern, all right? So that would be local to the country of Haiti and the neighboring country of the Dominican Republic, because it's a single island that is split. Let me see if I find another one that has Caribbean. All right. Caribbean. Okay. Here is Haiti, here is Dominican Republic, but it's the same island. It's part of the Upper Caribbean, and then the Lower Caribbean is known also as the Lesser Antilles down here. Basically, this will affect the pattern here, the weather pattern locally, regionally, all right? But not globally, because when we look at the Caribbean within, I wanted to see a world map. In the world map, well, we can go back to our map here. You know, the Caribbean in this map is a small area, okay? But it does affect locally quite a bit. And so I see people wearing masks in that news report, but that may be not because of COVID, but because of the contaminated air that is around, right? Now, ironically, I hope you're aware, Father Franco, that there is also a hurricane coming your way, right? So you have now a natural phenomenon on top of the human phenomenon, which is, where was I? Yes, there is a hurricane that it's called Fiona, I think it is, right? Look it up. Fiona is now going through this region more or less. I think it's approaching Puerto Rico, and it's coming your way. It's projected to go north of Dominican Republic and head into basically the Bahamas. But that hurricane, ironically, providentially, is going to help as it moves through to clear the air, literally the atmosphere of Haiti, all right, as it moves through. But while it's moving through, especially if it veers a little bit to the south, it's going to impact. It's going to bring nasty weather to Haiti, all right? So look out, try to get on the NOAA, N-O-A-A weather pattern. It should be for free because this is national, is the National Oceanographic and Atmospheric Administration. Anyway, where is latest news? Come on. This, no. Anyway, NOAA should have what's going on. You can search this site. I don't want to take time right now, but you can search the site for tracing Fiona. You have it live. Okay, what's the site, Antonio?
It's the same as that one.
Yeah. Where did you click? You
I just picked Miami. It should show like
here, Miami, maybe. Let's try that, or Fiona.
maybe the same.
First one. Try. Yeah. Okay, there you go. All right. Some are actually live, because that's an actual photo, aerial photo superimposed on the continents. Can we make it bigger? No. Anyway, here's Fiona, here's Puerto Rico, here's Haiti, all right. But the pattern, okay, this is what I was looking for. Come on, get bigger. Let me try.
Are we in some kind of
Not yet. It's known as the cone of projection. The cone of projection. All right. So it's gonna pixelate because I'm just amplifying the screen. But there. All right, we can still see blurry. It's not your glasses, okay? It started out here. This in red is Puerto Rico again. It's gonna get hit. I mean, every year. Here is the cone of projection, right? You can download it on your phone also, NOAA map.
Other trophies, so they can do those projections due to the convection currents and.
No, these projections are, it's complicated, but this projection is mostly done by data from previous hurricanes, accumulated crunch data. And then they do factor in the Hadley cell, for example, what's it doing now, but mostly they're looking at lows and highs, right? They're looking at lows and highs of the barometer, where, because they're gonna be, there's barometric pressure occurring all around this area. So the hurricane is going to find a path of least resistance. It's a low pressure, we know, it's a low pressure system, right? And it's going to be moving through a path of least resistance, all right? Until eventually it dissipates. But it's a formula that uses several factors, the data, historical data of previous hurricanes, the pattern of Hadley cells, but most importantly, the barometric pressure around the low cell. This guy should be rotating counterclockwise like that, all right? And so that's the pattern. The next few days, Sunday, Monday, Tuesday, Wednesday by Wednesday, between Wednesday and Thursday, it would be parallel to Miami, but on the east side of the Bahamas, which is a good thing for us. The ones that are going to get it, according to this projection, definitely Puerto Rico, especially the western half of Puerto Rico, then Dominican Republic, the eastern half of the Dominican Republic, especially the coastline, not directly Haiti, according to this projection, but indirectly, this is actually going to suck, because it's low pressure, it's going to suck weather in. So it's going to make clear weather for Haiti, high pressure. The weather should be moving from Haiti into the low pressure system, okay? So it's going to get clear skies. Bottom line, what I'm trying to say is that this system going through between Monday and Tuesday should clear the air for Haiti, including the burning tires and all that pollution that is occurring right now. And then that weather, that polluted air, if you will, is going to get mixed into the big system of the hurricane and swirl around, and it will dissipate eventually. But yes, the burning tires is contributing to the increase in CO2, because that smoke that we see, that's CO2, okay? And other toxic gases that are going into the atmosphere. Okay, so it's real, it's dramatic, it's happening right now. And yet we have to put it in perspective that weather is one thing, climate is another. Long-term accumulation of weather data will eventually become climate and will impact climate toward a tropicalization or toward a winterization. Okay, well, I'll talk more about the rights, but anything that keeps us alive, we have a natural right to air and to clean air, to breathe. The Vatican has been talking about this, Pope Francis in particular, who's placed a lot of emphasis on the environment, all right, and consciousness about the environment. So, but all recent popes really have spoken about the natural rights to air, to clean water, to a place to live, etc., etc. Okay, we'll crunch all this when we get to the topic of human population on Earth.
I don't mean to bother, but why there is so much resistance? And maybe this is not the right moment, but why there's so much resistance to really talk about this in our church?
Why was there resistance to Darwin's theory 200 years ago, 150 years ago? Because of the conventions, not convection as in currents, but convention. Convention is the state of the art today, you know, the ethos, the culture, the ethical culture. We need to catch up. We need to, anything that is new, that is recent, that is insight, that is new information tends to threaten us. And so where fossil records of humans, when fossils, not the record, but actual fossils of humans were discovered, it challenged us, you know. And at the beginning, even scientists, some scientists were saying, no, these are monkey fossils, these are not human fossils, and so forth. Or when dinosaur fossils started appearing, I mean, we're going back centuries. No, those are rock formations. Those are not really bones, you know, or they're recent bones. They're not, and then we dated them to millions of years ago. Whoops, it turns out that yes, there were animals millions of years ago. There were animals in Pangaea. That's exciting. There were animals and plants in Pangaea already. So when the continents fragmented, plants and animals went with those rafts to wherever they went, to a different weather, to a different climate, and they evolved independently. Okay, so the resistance comes on one part mostly from ignorance and fear and being challenged. It rocks our cage, right? It rattles our cage, as they say. It rattles our intellectual and our spiritual cage. And on the other side, also because of manipulation of ideologies. Okay, because we cannot shut down industry. Fossil fuel is still the cheapest fuel today. So if you want to pay $2,000 for a pound of rice, then make everything electric, you know, and shut down fossil fuel. But then we're going to be paying $5,000 for a cup of coffee because non-renewable energy is still too expensive. So it gets, see, technology overlaps with economy, and economy overlaps with politics. And then we get into politics, then it's all over the place, you know, because it's political spin and what's going to get me reelected. All right, first elected and then reelected. More to come. Folks, thanks again. Great to see you physically or virtually. And we'll continue next time with the hydrosphere. Okay?
Thank you, Father.
Thank you, Father.
Thanks, everybody.
Have a good weekend, everybody.
Thank you. Thanks a lot, everybody. Bye.
Dr. Chopi.
Yeah. Any question, or was that a bye-bye?
Sarah.
Oh, yeah. Okay. Do you have a question, or was that a bye-bye?
I just wanted to know that I was having connection issues, and that's why I was a little late to the Zoom.
Oh, okay. Yeah, I noticed it was in and out. All right. So not to worry, because I'm now going to close this and make it a YouTube and send you the link. All right.
Thank you.
Okay. You're welcome. Bye.
Thank you, Father.
Thank you. Thank you.